We are on the line.
Ok, bom dia todo mundo, bem-vindo a mais uma sessão de On Linguistics. Hoje a gente está recebendo a professora Marina Bedny. Bem-vindo, Marina. Ela se formou em uma série de instituições impressionantes, como a Universidade de Pensilvânia, na qual ela fez seu PhD em psicologia experimental. Ela também passou pela Hopkins University, na qual estudou ciência cognitiva, e no Harvard Medical School. Atualmente, ela trabalha na Universidade de Johns Hopkins, né, como professora e pesquisadora no Departamento de Psicologia e Neurociências. O nome em inglês é The Psychological and Brain Science Department. Sobre o trabalho dela, né, uma pergunta importante no trabalho dela é de como a experiência contribui para o desenvolvimento de funções cognitivas de alta complexidade. O laboratório dela tenta responder essas perguntas comparando as mentes e cérebros de pessoas com diversas experiências, como, por exemplo, as pessoas cegas. Elas investigam funções cognitivas no córtex visual de pessoas cegas desde o nascimento ou aquelas que se tornaram cegas quando adultas. Também investigam conhecimento de conceitos visuais nessa população. Um outro interesse mais amplo é como o cérebro humano incorpora conhecimento cultural e expertise, como leitura, programação de computador, etc., sempre contrastando o papel de experiência com a fisiologia intrínseca humana. Então, agora vou passar a palavra para a Marina. Então, Marina, please. Start your presentation. Just one remark for practical purposes. Pessoal, se vocês tiverem alguma dúvida durante a apresentação, por favor, colocam aí seu comentário, né, assim, no chat do YouTube. Dependendo da dúvida, eu combinei com a Marina que eu vou avisá-la, né, assim, se for uma dúvida que impede o entendimento. E se você tem, assim, uma curiosidade, uma pergunta, né, assim, que você gostaria de ter a opinião, a perspectiva dela, também coloca no chat, que no final da apresentação teremos oportunidade, né, dela responder as perguntas, assim, digamos assim, as perguntas mais, assim, de curiosidade, tá bom? Please, you can start.
Thank you so much. Unfortunately, I didn't understand what you were saying, but it sounded like a wonderful introduction. I could catch a few words here and there. Thank you, Marije. It's really wonderful to be here. Thank you for inviting me, and I can't wait to tell you a little bit about our work. So let me get started. So today I'm going to talk to you about this idea of nature, nurture, and neurocognitive development. So this is the question that has really inspired me to become a cognitive neuroscientist and a psychologist, is trying to understand how our early experiences and experiences in general contribute to our mind and brain relative to the innate predispositions that we come to the world with. Today, I'm going to talk about a particular subset of this work, focusing on language, right? And the particular insights into how language transforms the brain and how linguistic experience actually changes our mind. But the general theme is nature and nurture and experience. Before I start talking, I want to highlight the many students and postdocs that contributed to this work. Over this past year, we were very fortunate to have Emily Silvano, one of your co-students, be participating in our lab. And so we're very excited to continue collaborating with her, but I just want to acknowledge the work of all these students and postdocs in making this research possible. So what is the question that I'm interested in? So we're interested in the role of experience in neurocognitive development. And the way that our lab approaches this question is thinking about how our brain adapts to the varying circumstances that we find ourselves in. So one of the amazing things about people is that we're all smart, and we all have language, and we all have social capacities, but at the same time, there's a lot of variety in the kind of living circumstances that we find ourselves in, and we're incredibly adaptable, right? So, people live successfully in the Arctic, in the desert, in New York City, doing all sorts of things like programming computers or living as a blind adult that we don't think our brains specifically evolved for, right? And so the question that we're interested in is, how does the brain adapt? What makes the human brain so adaptable, and how does it do that? So most of the research that I'm going to talk to you about today is based on one particular population of people that we've been working with, which is individuals who are blind. Most of the work that I will tell you about is with people who are born blind. So these are people who grow up without vision. And we have worked with this population to understand the role of visual experience in shaping the mind and brain. And there are many things that you can learn from working with this population and from working with people who are blind. And I'm going to talk to you about two examples of the kinds of things that we worked on. One is visual cortex plasticity. So in humans and in primates in general, a very big part of our brain, maybe a fifth or a quarter, has evolved for visual perception. And so one of the things that I'm going to talk to you about is what happens to this part of the brain in people who never see, right? In a brain that doesn't see. And what I'll show you is that this part of the brain adapts and actually takes on language functions in this population. And we can think about what that means. And then the other part of what I'm going to tell you about is what vision tells us about the world, right? So as humans and as primates, as people, those of us who use our eyes around the world, right, to learn things, we see faces, we see objects, we see things far in the distance, scenes, right? We learn a lot about the world by looking at it with our eyes. So the question is, how do people who are blind learn? And in particular, what I'm going to focus on is what do blind people know about phenomena that you can only know through your senses visually, like color, light, and visual perception, to understand what is the role of sensory experience on the one hand, and then language and thinking in learning about the role about the world on the other. So hopefully it'll become more clear as I talk in specifics. So I'm going to start by talking about brain plasticity and about how language transforms the brain, and in particular about the repurposing of visual cortex for language and higher cognitive functions. So first, let me tell you a little bit more about the people who participate in the research studies that I'm going to talk about. These are individuals who are blind from birth, so they're born blind, and they're blind due to some problem with their eyes or optic nerves, so not due to brain damage. Since we're interested in the effects of visual experience on brain development and cognition, we're working with people who don't see, but not due to brain damage. These individuals have at most minimal light perception, so they cannot see colors, shape, or motion, and they never have seen those things. And these individuals are otherwise typically developing, right? These are individuals who have no cognitive or neurological disabilities. It's a very diverse population of people. We have lawyers and stay-home moms and computer programmers and students. All sorts of people come into the lab who are blind and are generously give us their time to participate in our research. These individuals do cognitive tasks in the lab. We use standardized tests, and we match our sighted and blind participants on these standardized tasks. So I will tell you mostly about data from these congenitally blind adults, but I will also always compare the results from blind adults to control populations. So in particular, we're going to match the blind participants to sighted controls who are matched in age and education, and sometimes in other cognitive characteristics to the blind participants. And for all of the experiments, the people who are sighted are blindfolded. Okay, so what we want to know about is the effects of the life history of the person, not the current state. So when we put a blind person or a sighted person in the scanner, they wear a light exclusion blindfold. So we're measuring responses in the brain, and the differences between the two groups are not because one group can't see and one group can. It's because of something previous to that. And then towards the middle of the talk, I'll tell you just one case about a comparison condition with people who lost their vision as adults, right? So this tells us something about what is the difference between early life experience, right? Experiences that you have as a baby, as a child, and when your brain is flexible, versus the same kind of experience, but at a different time in your life, namely as an adult, okay? So we could talk about that as we go on. So as I mentioned, the first thing that I want to tell you about is plasticity in the visual cortex, right? So in people who are sighted, this part of the brain, the visual cortex, occipital cortex, responds to things like spatial position, the orientation of lines, the color of stimuli, their brightness, their patterns. So this is the part of the brain that is involved in visual perception, right, in sighted people. And we can ask, what happens to this part of the brain in people who are born blind? And people have a lot of hypotheses about this, right? And the question is, how flexible is the visual part of the brain? One idea is that, and what people thought about 30 years ago is that it would do nothing. It would just atrophy. In a person who is born blind, this visual part of the brain would do nothing. And that's a very kind of static view of the brain, that each brain area evolves to do one thing, and it can only do that thing. We've known for 40 years, 30 years that that's not correct, right? That in fact the visual part of the brain in people who are blind take on other functions that are not vision, and responds to sound and touch. And what scientists have been trying to figure out for the past 30 years is, what kind of functions? How are they related to vision? How similar are they to their original visual functions? Are they also spatial functions? Are they also discrimination functions that are similar? So they're in another modality like audition or touch, but actually they're pretty similar to vision, or are they very different from vision? Okay. And so there's a lot of debate about this still in the literature. So I'm going to present you with one set of data and one perspective, but there's a lot of debate about this still in the literature. So what our lab has been interested in particular in the case of blindness, is the takeover of visual cortices by higher cognitive functions, one of which appears to be language. So this is a study that we did now a few years ago with Connor Lane. And actually, I started doing this work when I was a postdoc in Rebecca Sachs's lab. So in this experiment, what Connor did is he presented blind participants and sighted participants with auditorily played sentences while they are in an MRI scanner, right? So blind and sighted people are lying in an MRI scanner, and they hear the actress that the creator of the gritty HBO crime series admires often improves her lines, right? So they heard sentences, and then in a control condition, the participants hear lists of non-words, like tis naslis radi venerable galag uxlis vin ven zu. Okay, so right. So it's a list of words that these are English speakers, so it follows the phonological rules of English, but it doesn't mean anything, right? And has no grammatical structure and no meaning. So what we did in this experiment, and I'll tell you some more details, but in the first thing that we do is we look at what parts of the brain respond more to sentences than the lists of non-words. And what the participants are doing in the scanner is that they listen to the sentence, and then they get a question that they have to answer, like, is the actress is it the actress that admires the creator, right? So in our experiment, the sentences always, the questions are always who did what to whom. So we kind of push the participants to pay attention to the structure, right? To get the meaning from the structure of the sentence. And for the non-words, they're doing a memory task. So they hear another set of non-words, and then they have to say, is it matched? Is it similar to the previous long list that they saw? And I can tell you more about that task, but basically it's a memory task. So we compare these two conditions to each other. So we say, what parts of the brain are more active for sentences than non-words? This is like a standard contrast that people do in these kinds of studies. And what you find in sighted people and in blind people is that the very canonical, now well-known network of Broca's area, Wernicke's area, lateral temporal, prefrontal, left lateralized network is activated more for sentences than for non-words. What is exciting to us is that in people who are blind, you also find very large responses in visual cortex to sentences more than non-words. So you can see that at the bottom of your figure where it says blind, and there's like a little circle around the visual cortex. So the left is showing the lateral view of the brain, the right is showing the medial view of the brain. And you can see that the blind participants have more activity, right? They have this activation in the visual cortex. So the other thing that Connor did in the study is that he actually included two kinds of sentences with syntactic movement, and then match sentences but without that syntactic movement. And you can read the sentences to yourself so you can kind of see what they felt like. So the top sentence in dark red is a sentence with syntactic movement. The bottom sentence is the same sentence but without syntactic movement. And we inserted this manipulation to see, is the visual cortex of people who are blind just activating for sentences, but is it actually sensitive to fine-grained linguistic information? And it turns out that it is. So the plot that I'm showing you on the right, the one that shows that continuous percent signal change bar, is showing that the two sentence conditions, the pink condition and the red condition, are different from each other. So when the participants are listening to the sentences, the visual cortex responds more to the grammatically complex sentences than the simpler sentences, and more to both kinds of sentences than to the non-word control. And in sighted people, you do not see this effect, right? So the visual cortex of people who are sighted, even when they have their eyes closed, doesn't care about this, whether the sentence has syntactic movement in it. So I think this is pretty exciting and interesting, and it suggests that the visual cortex of people who are blind is becoming responsive to linguistic information. One really interesting thing that we saw in this study is that those blind participants who showed a bigger difference between the plus move, the grammatically complex, and the minus move, the grammatically simple sentences, also performed a bit better on the task. So they also were better at answering comprehension questions about the grammatically complex sentences. So that's kind of interesting. It's not conclusive evidence, but it suggests that maybe this part of the brain is actually behaviorally relevant to the understanding of these sentences in this blind population, although it's not conclusive evidence to this effect. But we could talk more about why, and we're continuing to work on this problem. Now I'm gonna switch gears for a second. If there are any questions about this, this would be a good time. If anybody wants to interrupt and pipe in and ask for any clarification questions before I keep going. Okay, then I'm going to keep going. So the next thing that I want to tell you about is we did the same study. So this is the work of Rashi Pant, who was a research assistant in our lab and is now a graduate student working with Dr. Bridget Roeder in Germany. So Rashi recruited a group of participants who became blind as adults. This actually is not an easy thing to do because we needed to match the adult onset blind participants to the congenitally blind participants in terms of how much vision loss they had. And we were looking for people who had lost their vision suddenly so that we could be sure when they actually lost their vision. So this was quite a tricky population to recruit, but she did it. So in this study, she did the same sentence task, but now with people who are become blind as adults. So to start with, I'm showing you the results from the previous study, but now instead of graphing them as like this percent signal change, I just graph them as a bar graph. And I'm showing you two representative visual areas in people who are blind. One is primary visual cortex, one is secondary visual cortex. The dark blue bar is the grammatically complex sentences, the light blue bar is the simpler sentences, and the gray bar is the non-words, okay? And so this is the same thing I showed you before, which is that in congenitally blind people, the visual cortex responds more to sentences than non-words and more to grammatically complex sentences than simple ones. But in the sighted people, who's shown on the left, you don't see that effect. There's not much response at all, and there's not a grammatical complexity effect, okay? So now what happens in people who are adult onset blind? Are they more like the congenitally blind group, or are they more like the sighted group? Whoops. And what we find is that they're more like the sighted group. So these are people, some of whom have been blind for, 40 years. On average, I believe they were blind around 15 years, but at least 5. But their visual system is still more like that of a sighted person than that of a blind person. So you can see that in primary visual cortex, there's more activity to the sentences than there is in sighted people, right? So there's some change happening over time, but we don't see that grammatical complexity effect that we saw in people who are congenitally blind. So this suggests that really this part of the brain is highly flexible, but only during this early childhood period. And this effect that I'm showing you here for language, we and other people have seen also for other cognitive functions that invade the visual cortex. So language is not the only function that invades the visual cortex, and I'll talk about that in a second. But in all cases, it seems like the effects are always much larger and qualitatively different in people who are born blind than in people who are adult onset blind, so who lose their vision as adults. Okay. So, so far I've told you about responses to language in the visual cortex, but I want to make sure and make it clear that language is not the only thing that activates the visual cortex in people who are blind. And so I'll give you another example from our own research. This is work by Shipra Kangelia, who did her PhD in our laboratory, and she's now a postdoc in Jessica Cantlin's lab. So Shipra has always been interested in number. She's interested in mathematics and how the brain and mind does numerical cognition. So in this experiment, she compared language to math, right? So participants, again, in the MRI scanner, heard pairs of math equations like 7 minus 2 equals x and 9 minus 5 equals x, and had to decide whether the value of x is the same across those two equations. And then in a language condition, they would hear pairs of sentences, one in passive voice, one in active voice, and they have to decide whether they mean the same thing, okay? So what I'm showing you right now on the brain map is responses in sighted people. The red is more for math than language, and the blue is more for language than math. So the red areas are the ones that respond more to math than to the sentences, and the blue areas respond more to the sentences than to the equations. And this effect in the sighted is a replication of previous studies. So we had modeled this experiment based on previous work, and now we are replicating. And it is well known that the intraparietal sulcus, which is here in the parietal cortex, responds to numerical information. Right? It seems to play an important role in this function. What we found in the blind participants, what Shipra found in the blind participants, is in addition to this parietal response, blind individuals recruit visual cortices for the math task, right? So when you look at the back of the brain, which is shown on the left. So it's, if you go from the left, the second column from the left, you see the back of the brain, the left and right hemisphere, and you can see in the blind subjects, there's this additional patch of red. So that's the visual cortex responding more to equations than to sentences, which is very cool. Whoops. So the bottom row of data is actually a group by condition interaction effect. So that's showing the difference between blind and sighted people. And it makes it a little clearer what parts of the brain are responding to math and what parts of the brain are responding to language in the visual cortex. So you can see that in the visual cortex for blind people, there are some patches that respond to math. And then there are different parts of the visual system shown in blue that are responding to sentences. Okay, so here's a more detailed look at these effects. So first of all, in addition to just including equations, one of the things that Shipra did is manipulate the difficulty of these equations. So she made the numbers bigger, or she moved the x to the wrong side, right? So using this strategy, she manipulated how hard the equations were. So some equations were things like x minus 12 equals 17. That's the hardest equation. The easiest equation would be something like 7 minus 2 equals x. And what's interesting is, just like the language responsive part of the visual cortex, the number responsive part of the visual cortex in blind people responds more to the hard math equations, right? So again, what this suggests is that these repurposed plastic parts of the visual cortex in this population, they're not just overall activating for the task, they show subtle differences in activation that are related to the cognitive properties of the stimuli to which they're responding, okay? And what I'm showing you here is in red, the parts of the visual cortex that are responsive to math, and in blue, the parts of the visual cortex that are responsive to language in these blind individuals. So again, the emphasis here is that there are different parts of the visual cortex are responding to different higher cognitive functions in these blind participants. Again, these are all auditory stimuli, right? So they're getting repurposed for something else. And I don't have too much time to talk to you about it today, because I want to get to the other research that I want to tell you about, but we have some ideas about why these particular areas get repurposed, and it seems to be related, at least partially, to the connectivity patterns in the brain, right? So it seems like the parts of the visual cortex that are responding to number also have, at least functionally, stronger connectivity with parietal number areas and prefrontal number areas, whereas the parts responding to language have stronger connectivity with prefrontal language areas functionally, right? So there's an interaction between the innate predispositions of these brain areas at birth, but also their incredible flexibility, where in a blind person, they repurpose to do these higher cognitive functions. Okay. One quick thing, the last thing that I will say about this plasticity question is, one question we can ask ourselves: does this change blind people's behavior? So blind people are recruiting parts of visual cortex for other cognitive functions, including language, but does this matter for behavior, or are they just activating? Okay. And this is a very difficult question to answer with the tools that we have right now. So I won't give you a full answer. I will only give you a partial answer. So there's a little bit of evidence that we have that people who are blind on some tasks perform better than people who are sighted. So this is an example of work done by Karen Arkos and Nora Harhen. Actually, this paper just came out if you want to read it, and I can send it to you. So in this study, what Karen and Nora together with Rita showed is that people who are blind have superior verbal memory relative to people who are sighted. This has actually been shown before, so they're replicating this effect. They can remember more lists of letters, more lists of numbers, more lists of words, right? In this experiment, we're using letter lists, so blind people can remember more consonants, but they don't remember more just sounds, right? So it seems to be particular to verbal information. So blind people are better at remembering verbal material like letters, words, numbers, but not better than sighted people at remembering just sound, meaningless sounds like that you can't put labels to, right? So that's one piece of evidence that people who are blind show some advantages in verbal behavior. Something more close to what we were talking about is another study done by Rita Loyotile together with Connor Lane. Again, showing that people who are blind show better performance at answering comprehension questions about grammatically complex sentences. So in this experiment, we tested 50 sighted controls, 51 sighted controls, and 24 congenitally blind adults. The study took a while to do because it requires very careful matching of the congenitally blind adults to the sighted adults, and we only for this study tested young congenitally and blind and sighted adults to try to restrict the amount of variation on these measurements. But what we found in this study is that blind participants are better at answering comprehension questions about grammatically complex sentences. The task that they're doing here is the same one that I showed you before that participants did in the scanner, but now they're doing it, in a room, not in the scanner, because it's hard to measure behavior very carefully inside the scanner because it's very noisy and people are kind of exhausted. So the blue lines is performance by blind people, and on the left is the performance for sentence processing, and you can see the blind participants are responding more accurately for complex sentences than the orange bar, which is sighted people. And on the right, what I'm showing you is various control measurements that we took in the same participants, including their reading ability, their vocabulary, their math ability, to show that these groups of people are not different in general. It's not that we just happen to pick a group of blind people who are smarter than the sighted people. No, the blind participants have an advantage at auditory sentence comprehension. And actually, Emily Silvano is now doing a project in collaboration with our lab, trying to get more clearly at the bottom of this. Why are blind people better? So I kind of suggested, and it might be the case, that it's because blind people have extra visual cortex territory devoted to language, but we're not sure about that. So that's something that we need to follow up on. Maybe they're just getting better at sentence processing. From a more cognitive perspective, there are also questions about, are blind people better at reanalysis, for example? Are they better at reanalyzing the sentences rapidly? Or are they better at online sentence processing? So what Emily's doing now is a self-paced listening and self-paced reading experiment in blind people to see when these benefits are actually occurring. So stay tuned and talk to Emily. The one quick thing that I will say is that we found in the study that the benefit for verbal memory and the benefit for sentences may not be the same, because there's the people who show the biggest benefit for sentences are not the same people that show the biggest benefit for verbal memory. So it suggests that these are maybe two separate improvements that blind people are showing. Okay. Let me take a break. How are we doing? Are there any questions before I go on? Because now I'm going to switch gears and talk about visual knowledge. Anyone? Are there any questions that need to be addressed now, or should they all be addressed later? Yeah. When comparing language to math, how do you measure the levels of complexity? Right, that's a good question. So we do not compare complexity across language and math. So we manipulate complexity within math, and we manipulate complexity within language, right? And then we compare language to math, but not complexity levels across them, because you're right, it would be it's not, how would you do that, right? Because they're completely different, completely different. We match overall, you can match the behavior for the math tasks and the language task, but that's not really, you know, it's like comparing apples and oranges, right? They're two different things. Yeah. Anything else? Okay, I'm going to go on. And I think actually I'm going to skip this. We have some work in the lab that's not on blindness, that's on computer programming and language's role in that, which I think is interesting. But if you want to hear about that, I'll have to be another time, because otherwise we'll have no time for anything. Okay. Right. So what I take from these data is that the human brain, the human cortex, is highly flexible at birth, right? When a human encounters themselves in a very different environment, so when a child is born blind, the parts of the brain that evolved for vision repurpose, right? So although the human brain has evolved specific adaptations, it is also has evolved to be very flexible, right? So that's one conclusion. Another conclusion is that language invades other cortical areas, right? So it doesn't just, there's not a static part of the brain that does language and nothing else ever does it, right? So it seems like language can transplant itself. It's not moving because still the other parts of the brain, like Broca's area and Wernicke's area, are still doing language in people who are blind. So it's not like it's hopping around, but it's spreading, right? It's spreading into areas where we don't usually see it. So I'm gonna switch gears now to something else that we work on with people who are blind, and that is what people who are blind know about visual ideas, visual concepts. And actually, this question, what people who are blind know about visual ideas, has a very long history in philosophy and also in psychology. So here I am giving you a quote from John Locke, who is an empiricist philosopher who wrote about blindness. And what he says is that, you know, you can read it to yourself, but what he says is that a blind person could never understand the ideas like rainbow or yellow, because, you know, if you don't experience it, then you can never truly understand them. You can talk to the blind person all day long, but never will they really understand what this means. And psychologists have been interested in this claim for a long time. So here I'm showing you the cover of a beautiful book written by Barbara Landau and Lila Gleitman in 1985 called Language and Experience, where they characterize learning of language by a blind child, Kelly, and a couple of other blind children. And so this research that I'm going to tell you about picks up on this tradition to try to understand what is the role of sensory experience versus language and innate predispositions in understanding visual ideas. So the first thing that I'm going to tell you about is a project on visual verbs, right? So this is a project that I did actually when I was a postdoc working with Rebecca Sachs. So in this project, what we asked was, to what degree do people who are blind and people who are sighted have the same meanings for visual verbs? And we looked at two kinds of visual verbs. Verbs of visual perception, like glimpse, look, watch, gawk, peek, glance, leer, gaze, peer, scan, and so on. And also verbs of light emission, like sparkle, glitter, glow, flicker. And then we compared these verbs to control categories, which we expected to be the same across blind and sighted people. One was a touch category, so touch perception verbs, amodal verbs of perception like admire, enjoy, notice, perceive. And on the emission side, we looked at verbs like beep, boom, buzz, chime, gurgle, so sound emission verbs, and also motion verbs, okay? So in this experiment, we asked blind and sighted participants to judge the semantic similarity of pairs of words. And verbs are always being paired only within their broad grammatical class. So we're never going to pair a verb like glimpse with a verb like blaze because they're so different. It's may not get much sense out of those kinds of judgments. It's always within a broad grammatical class. But then we pair all the words with each other. And so the participants are actually making thousands of semantic similarity judgments. The study was done online, and participants would log into the website. They would respond to these questions. Then they would log out, and then they would come back later on. So out of these kinds of judgments, we get for each pair of words like glimpse and look, or glimpse and glance, or glimpse and gaze, we get a number which corresponds how similar are they. And then we get the same thing for glimpse and touch, or glimpse and caress, and glimpse and admire. Okay, and so we can generate what we call semantic similarity, what are called semantic similarity matrices, which reflect which verbs are most similar. Okay, so that's what you see in the bottom right hand corner. So and you can see already if you just look at the matrix, so every little square in that bottom right hand corner is a pair of words. Okay, and so you can already see that, or maybe you can't because the words are too small. The visual verbs are more similar to each other for this particular person. So this is data from one person than they are to touch verbs, right? So we use these kinds of data to do various kinds of analyses. So this analysis is a multidimensional scaling analysis where we reduce the data to 2 dimensions, and we ask whether blind and sighted people have similar dimensions and whether the verbs from these different classes fall into the same places on these dimensions for these 2 different groups. And so what you can see qualitatively anyway, and it's true quantitatively as well, is that people who are blind treat visual verbs like peek and glimpse and gawk as a class. They think of them as similar to each other, different from tactile verbs, and different from amodal perception verbs, right? So the responses of the blind and sighted people are exactly the same here. And in the bottom right-hand corner, you can see a correlation analysis of the same data. So here what we did is we measured the same data in 2 groups of sighted people, and then 1 group of sighted people and 1 group of blind people. And what you can see is that when you correlate 2 groups of sighted people and then 1 group of blind people and 1 group of sighted people, the correlation is exactly the same. So 2 groups of sighted people are just as similar as a blind group is to a sighted group on these verb meanings. And this is an individual analysis of individual participants. The bottom line is that's the same. So I'm going to try to move forward because we're kind of running low on time. We find the same thing for the light verbs, right? For verbs like glow and flash or glow and shine. Blind people's meanings and sighted people's meanings measured in this way are exactly the same. And the kinds of things that blind people know, shown by this multidimensional scaling plot, is the kinds of things that linguists already say that these verbs contain, right? So linguists have pointed out that verbs of light emission are have an intensity dimension, right? So a verb like glimmer is a low intensity verb, and a verb like flare is a high intensity verb. Linguists have also a verb like flash is a high intensity verb. Linguists has also pointed out that another dimension that's really relevant to light emission verbs is stability, right? So some verbs are stable, like glow, and some verbs are unstable, like flash. And blind and sighted people's meanings line up exactly on these dimensions, right? So despite not ever seeing themselves, people who are blind have the similar meanings to people who are sighted. One question you might ask yourself when you see these kinds of data is whether people who are blind are, they sound like they know the meanings, right? They're using the words the same, they respond as if they know the word meanings, but do they really have the same meaning, right? that's a very difficult question to answer for any two people. How do we know that any two people really have the same meaning in their head, right? As psychologists. But one kind of data that we use is neuroimaging data, right? So we can ask, are blind and sighted people using the same neural mechanisms to process these kinds of words? So this is a study that was done by Julia Ellie and Connor Lane, and actually Miriam Hauptmann is also collaborating on this work. So here, blind and sighted participants do the same semantic similarity judgment task, but now they're doing it in an MRI scanner. And what I'm showing you here is data from blind and sighted people when comparing verbs to nouns, right? So what we find, and other people have found as well, is that the left middle temporal gyrus of the brain responds more to verbs than nouns in sighted people. And we find the same effect in people who are blind for concrete words, concrete verbs like light verbs, sound verbs, hand verbs, and mouth verbs. And what we did as well, and what Julia Ellie did and what Miriam Hauptmann is doing, is to look at patterns of activity in this verb area. And what she can find is that patterns of activity inside this verb area distinguish different verb classes from each other. And they do that in a similar way in people who are blind and people who are sighted. Okay, I'm sorry I'm going through this rather fast. So the other thing that I wanted to quickly show you is that if we separate the verbs out, so we have one column for the light verbs, one column for the sound verbs, one column for the hand verbs, and one column for the mouth verbs, shown in different gradations of red. This verb area in the blind subjects responds to light verbs just as much as to all the other verbs, and in the same way as it does in sighted people. So this is a part of the brain that is resilient to blindness. So it represents, we hypothesize it represents the meanings of these light verbs. And it doesn't care whether you've never ever seen any light and you've never seen anything in your life. It develops in the same way. Okay. All right. Should I take a question? Is there anybody? I feel like I did that really, really fast. Okay, I'm going to keep going. How much time do I have actually, so I know what to tell you guys about next? Is there any, can someone say how long would you like me to keep talking for? Oh, let's see if I have, oh. Okay, well, I will keep going. But if someone wants to, so if I start to run over, oh, I see 50 minutes. Okay, great. Awesome. I will be done by then. Great. All right. So, right. Okay. So let's see how fast I can do this. Yeah. All right. So, so far I've told you about words, right? But of course, I don't need to tell you, words are just the beginning. And so there's much more to meaning and to language. So one question we can ask is whether people who are blind make same kind of inferences as sighted people based on sentences about vision, or whether they have the same words for visual meanings, but actually when you get into more complex meanings, compositional meanings, and inferential thinking, whether then there are differences among blind and sighted people. So in this project that I'm going to tell you about next, what we did is we used visual verbs in sentences, and we specifically looked at how people who are blind make inferences about visibility, and whether those inferences are similar across blind and sighted people. So look at this scenario, right? Here goes a woman, she's walking, right? And then she glances at another person standing at the station, right? So when you see this kind of scene, you might have all sorts of thoughts like, do you think she knows whether that's a man or a woman? Do you think she knows whether he's wearing a hat? Does she know the color of his eyes? Does she know how old he is, right? So you have probably a bunch of intuitions about things that she might infer from this kind of experience. And the question is, where did you get those intuitions? How did you learn that? Do you have to have visual experience yourself? Is the way that you learn that about this woman because you yourself see? Or is it possible for you, even if you have never seen anything in your life, to have similar kinds of intuitions? Okay, so in this experiment, Lisa Moos and actually now Zuen Wen is collaborating on this project as well. She presented blind and sighted people with scenarios where they were asked to make inferences about visibility. So for example, they heard things like, Sarah is a sighted adult. She was walking to the grocery store and walked past a brick row home that was right up against the sidewalk. A person was sitting in front of the stoop of the row home. Sarah glanced at this person as she walked by them and then kept going. Based on what she saw, how likely is Sarah to know whether the person is smiling or frowning, right? So we asked a bunch of questions like, how likely is she to know whether they're smiling? How likely is she to know whether they're wearing a hat? How likely is she to know whether the person is 30 or 60 years old, whether the person is feeling sad or happy, whether they have light blue or dark brown eyes? So we asked all these questions from the participants, and they had to respond to them by rating on a scale of 1 to 5. Okay. And then in a control condition, participants heard analogous scenarios, but now about hearing. Okay. And so I won't go into details, but we now have the same hearing scenarios. So does she know how old the person is? Does she know if they've been crying? Does she know if they have a British or an American accent? Do you know whether they're eating while they're talking, right? So things you might be able to tell from a hearing scenario. So here I'm showing you the correlation between data from blind people on the y-axis and sighted people on the x-axis for hearing scenarios. And their judgments are very highly correlated. So not surprisingly, right? Sighted people and blind people agree very well about whether you would be able to tell whether somebody was wearing a hat by talking to them. And the answer is no, you would not, right? Because you're talking to them, but you would be able to tell whether they have a British accent, right? But what's more interesting is that the judgments are also highly correlated for seeing scenarios, which is amazing, right? Which suggests that you don't need to see yourself to make these kinds of judgments. One interesting thing that we looked at is how, this is a COVID picture. I apologize for that, but there's a lot of distance questions now. So we looked at the question of how distance and time affects perception. So now we are manipulating, right? So the verbs that I was telling you about, some of them contain information about time. So for example, I stared at something or I glanced at something. So how does that influence whether I was able to see something or not? And alternatively, we could say, oh, I looked at somebody across the street versus I looked at somebody standing right next to me. How does that affect whether I think it's perceptible or not? Okay. And these are the kinds of scenarios we gave people where we manipulated whether how close the two people are that are interacting or how long the looking experience is. And what you find, and so then we asked, how does distance and time influence the judgments of sighted and blind people? Does it influence them in the same way? And actually what we found is not exactly. So both sighted and blind people, and here I'm showing you data from sighted people, judge that the further away somebody is, the less likely you are to be able to see them. Okay, that's the orange bar. And the longer you look at somebody, the more likely you are to be able to see them. That's the green bar. Okay, so that's what I'm showing you here. Distance, so closer you are, the more likely you are to see them. Longer you look, the more likely you are to see them. And that's true in blind people as well. Those are the bars on the right. But people who are blind weight time more than distance, whereas in people who are sighted, weight distance more than time, right? So this gives us a little example that although blind and sighted people have generally similar understanding of how seeing works, there's some subtle differences that seem to have to do with first-person sensory experience. And what you find is that in the hearing control condition, blind and sighted people are similar. Okay, so this isn't just to do with anything; it's particular to seeing. So what this suggests is that blind people have very rich, sophisticated models of vision that they acquire by making inferences from what people say, right? But there are some subtle details of that model, the weighting of different parameters like distance and time, that actually are based on first-person experience and are a little bit different in people who are sighted than people who are blind, okay? So I'm going to skip the study and then tell you one more thing, and then I'm going to stop. Okay, so the last thing I want to tell you about is an analogous experiment, but in a different domain of vision. This is the work of Judy Sain Kim, who was a graduate student in my lab. And Judy did her PhD thesis on what people who are blind know about color. This paper is also now published, which I didn't change on my slide, but I can send that to you if you want to hear more details about it. So Judy was interested in what blind people know about color. Color is a particularly interesting domain because, again, it is this property that you can only experience visually, directly, right? And so the question is, what do people who are born blind know about color? And in this study, Judy tested two different aspects of color knowledge in the same blind participants. One aspect of color knowledge that she tested is something I'm going to call rote memory kind of color, right? So all of us, or many of us, agree that polar bears are white. School buses in the United States are yellow. I don't know what color they are in Brazil. Paper tends to be white. Cars can be all sorts of different colors. So this is one kind of knowledge we have about color, which is like which color is every object. But then the other kind of knowledge that Judy tested about color is how color works, our understanding of color, right? Why does a polar bear have that white color, right? So there's the rote knowledge and the understanding knowledge. And what I'm going to try to show you is that people who are blind know more about the understanding of color, agree with sighted people about how color works, but don't always agree about the particulars of which colors objects have. So Judy compared blind and sighted people's knowledge of color across three different kinds of object categories that developmental psychologists have studied. One is natural kinds. So these are things like polar bears and lemons and leaves that are products of nature. They could also be rocks and gems, right? And then the other category of objects she studied are artifacts like computers, cars, paper, or school buses, things that people make. And then these artifacts are actually divided into two further categories, which I'll tell you about in a second. So the first category here shown here in green are natural kinds like leaves. The next category are artifacts like cars. And these are now artifacts for which so I want to like test your intuition, right? For which color doesn't have any particular purpose. And then another category that she had is paper, for which color has a particular purpose. So let me make clear what I mean. So let's do this little quiz for yourself. First, I'm going to ask you this. What is a common color of a leaf? I want you to type it in the chat if you don't mind. And then I want to have you rate something on a scale. If you picked two leaves at random, how likely are they to be the same color? Okay, where 1 is not likely at all and 7 is very likely. Okay, could you please answer in the chat? That would be so great. Okay, so now we're going to do this task again. So now for cars, what is the common color of a car? Could type that in. But the next thing I want you to do is this rating question. If you picked 2 cars at random, how likely are they to be the same color? Where 1 is not at all likely and 7 is very likely. Could you please put that in the chat? That would be so great. So wonderful. So we did this task with sighted and blind participants, and what we found is hopefully what you all can see in the chat, which is that people tend to say that 2 leaves will be the same color, 2 natural kinds, whereas 2 cars can have any color, right? Because they're made by people. People select their colors based on, who knows, their preferences. So there's a lot more variety, and they're not likely to have the same color. And then the third kind of object we had is paper. And now paper, people pick the color of paper, but paper has a color for a particular purpose because we want to write on it. And we want to be able to see what we're writing. So it's an artifact, but it has a functional color. And so for paper, most people say, sighted people say, it's very likely to have the same color. And so in a control condition, we ask usage questions. Now we say, what is a common thing that you can do with a leaf? If you picked 2 people at random and asked them each to do something with a leaf, how likely are they to do the same thing? If you don't mind entering in the chat, where 1 is unlikely and 7 is very likely. How likely are 2 people to do the same thing with a leaf? And then we do the same thing for a car. If you pick 2 people at random and ask them each to do something with a car, how likely are they to do the same thing? Where 1 is unlikely and 7 is very likely, if you want to enter your responses in the chat. So what you find with this kind of task is that people say that for natural kinds, they're unlikely to do the same thing, but likely to do the same thing for artifacts, and the reverse for the color. The natural kinds, like a leaf, are very likely to have the same color, but the artifacts like cars are not likely to have the same color. And then paper is more like a natural kind in that it should have the same color if you pick 2 at random. So these are the data from sighted people. And what's, sorry, I'm gonna skip. What's interesting is that we get the same exact responses in people who are blind, right? So people who are blind, just like you just did, know that if you picked 2 leaves at random, they would likely have the same color. And if you pick 2 cars at random, they probably wouldn't have the same color. And if you pick 2 pieces of paper at random, they probably would have the same color. So the performance of sighted people and blind people on this task is the same. What is interesting is that sighted and blind people don't always agree on the particular color of the object. So even though blind and sighted people agree about the consistency of the object, there is disagreement between blind and sighted people about what the color of the object is. So I'll give you some examples to illustrate. So all sighted people said polar bears are white. But when we asked blind people what color polar bears are, a significant proportion of them, something like a quarter, said that they're black. And when we asked them to explain, they said it has to do with their climate and they need to absorb heat. So that's why they're black. And actually what I found out is that polar bears are black underneath their fur for this reason, which I didn't know until after this experiment. Another example is that some of our blind participants said that carrots are green, and it has to do with chlorophyll. So, plants are green. So this is an example, again, of a very rational, correct explanation, but not agreement on the same color. Some subset of our blind participants said that Mac computers, like the one I'm using to give you this talk right now, are red because Apple has a symbolism with red apples. So what we found in this study is that people who are blind have the same understanding of color, make the same inferences about color, but they don't agree with sighted people on exactly what the same colors are. The last quick thing to tell you is that in addition to doing that experiment with real objects, Judy invented this imaginary island. And so she did the same experiment for fake objects that nobody has ever experienced, like, Enleys and Canpas, and which were also natural kinds and artifacts with functions. And she again found that sighted and blind people perform the same. So it's not like blind people go around memorizing things about real objects. It's that they have a really in-depth understanding of how color works. Okay. So what does this mean? What I think this means is that you don't need sensory experience to develop really rich understanding. And in particular, I think this shows the power of linguistic communication to have sharing of ideas among people. And in particular, it suggests that language is better at aligning people's understanding and their intuitive theories of the world than sharing little facts like, Macs are silver and polar bears are white. So language is really much better at aligning our understanding than isolated facts. Okay, so just to conclude, people who are blind develop very rich understanding of visual phenomenon, including visual verbs, perception, light emission, color, have very rich understanding of visual ideas. For these kinds of concepts, sensory experience is not necessary. Language is a key way that people learn about the world. But we don't go around just memorizing what we hear. We make inferences based on the language we hear. It's a tool for learning about the world that enables blind people to learn. And that's it. So now I just want to wrap up and thank you guys for listening to me, to thank my lab who has done all this beautiful work. My collaborators. I want to also thank, very importantly, the blind community who has generously supported our research, and the participants who have given their time to make this research possible. And thank you so much for listening to this talk.
Thank you so much, Marina, for this wonderful talk. There were some questions during your presentation that I think have not been answered yet, and I have some questions as well.
I can't wait to hear them, so let's do it.
But I'll start with the question from one of the viewers. She asked, Barbara, in a matter of efficiency, how could we compare blind people's language acquisition and sighted people's, considering either mother language and second foreign language?
So I think, let me see if I can think through this question. So I think what you're asking is whether people born blind acquire language in the same way as sighted people. And I think this is a really interesting question. And actually, there was the participants in our studies so far have mostly been adults. We did a study with blind children some years ago now, most looking at neural development. But I will tell you what I know about that research, which is that, acquisition of language is different in blind and sighted people in a number of ways, right? So children who are blind don't have access to the same kind of access as their parents to some of the things that that are being talked about, like sun and the moon, right? Or the cow that's across the street. They don't see the same things that the sighted people are referring to, or yellow. Some really important work that I referenced in this talk by Barbara Landau and Lila Gleitman showed that remarkably, blind children are able to acquire language in very similar ways to sighted children despite this fact. So despite the fact that children who are blind don't have access to the reference of the things that are being talked about in the same way. Of course, blind children have other kinds of access, right? Like tactile access and auditory access. But despite no visual access, the acquisition of language in blind and sighted people is actually quite similar. And if you're more interested in that topic, then the Landau and Gleitman book is a must read. It's also just extremely enjoyable and clever. So that's the answer. I guess the other question is whether there's some increased ability for language acquisition in people who are blind, perhaps as a result of the recruitment of these other brain areas. So that's another question which I've thought about in relation to, you could think about in relation to second language acquisition, like are blind people better at learning other languages than people who are sighted? It's a tricky question to answer empirically, right? Because you have to control for so many things, but I think that it's an interesting question and an interesting prediction. Yeah. Oh, sorry, I don't hear you.
Should turn on the microphone.
Okay, now I can hear you. Yeah.
We don't have any other questions yet, so I'll take my opportunity and ask a question. I was wondering if you have any perspective or comments on theories of embodiment, so that place a high emphasis on the relation of the body to form concepts and also language.
Yeah, I mean, I think this work suggests that some versions, I mean, there's a lot of variety in embodiment theories and exactly what they claim, but I think this work suggests that there are some popular but extreme embodiment theories that cannot be right. They're wrong. They cannot account for these data at all. So I think sometimes, those theories focus on interesting differences between, like people with small variation in sensory experience, like somebody who is like an expert, player of hockey, or some subtle difference, in sensory experience. But the fact is that people who have completely different or very different sensory experiences, like people who are blind and sighted, have nearly identical concepts, right? So I think, and that's not just true for blindness. There's also work from people who are, for example, born without arms, have different tactile experience. There's less work on deafness, but that's another interesting area to look at. We have no evidence that people with different sensory experiences have any really deep difference between their sensory concepts, right? So I think the extreme versions of embodiment just can't be right. Like, it just doesn't get started. This theory doesn't work. So that's that's kind of a, yeah.
Okay, thank you for that. I have another question, and I'm going to hog the mic as long as I can.
Do it.
But please, people at home, ask us questions as well, because I'm sure you're curious, just like me. When you showed these results, these fMRI results from the beginning, right, where you compared these sentences, one of them were move and other were non-move, right, sentences, where you compared them for complexity, right, syntactic complexity. I thought that one of the complications of fMRI is that it's so late, right? It's a late reaction, so several cognitive aspects could be influencing there. And you could think of other characteristics, for example, that are relevant for those stimuli. For example, this non-move is like a sentence that might have the type of words that report on people's mental states or things like that, right? So I was wondering, how you understand those differences in terms of what is the difference. Obviously, you showed, right, the difference in activation in the visual cortex, but to what kind of functionality would you attribute this to? Whether you have some kind of intuition about this, or whether there is other evidence that supports some kind of interpretation. I was curious.
Yeah, great. I'm going to share the slide again with the stimuli. So I think there are kind of a bunch of pieces to your question. Can you guys see my slide?
Yes, we can.
Okay, great. So it is the case that MRI is very sluggish. And so one of the things that we don't know the answer to is whether, like when in processing, the visual cortex gets involved and the relative timing of that contribution to other areas like the temporal lobe. These questions are hard to answer, and hopefully in the future there will be some MEG experiments answering these kinds of questions. So the answer to the timing question, we don't know. The answer to the words question, so it is important to note that the sentences in these experiments contain the same words, right? So the plus move and the minus move sentences are lexically nearly identical, right? So it's across people, some people, half of the participants hear the sentence in the plus move condition, like the actress that the creator of the gritty HBO crime series admires often improves her lines, and half of the people hear it in the creator of the gritty HBO crime series admires that the actress often improves her lines. Same words, right? So it cannot be differences in the words. So I think there are some things that we have ruled out, right? It's not the imageability of the stimuli. We've analyzed that before, and there's no correlation between how imageable the sentence is and how much the response is. So I think we can be pretty sure that the visual cortices of blind people respond to sentences and are sensitive to their grammar, but exactly what they're doing, when they're doing it, and how it interacts with other parts of the brain that are also active, I think that remains to be determined. One interesting thing that we are very slowly trying to do, partly due to the pandemic, is to do some transcranial magnetic stimulation experiments where we present these sentences and then we apply TMS to the visual cortex while people are listening to them. So I think that would really help us to understand, is this activity behaviorally relevant, and at what point does it become behaviorally relevant, because TMS is very temporally resolved. So for sure, there's more work to be done to try to figure out exactly what are the processes that how the visual cortex is contributing. The other thing we don't know is, and this is true for not just blindness and visual cortex, but in general, right? Language recruits very large part of the brain. It includes prefrontal areas and lateral temporal areas. And in the temporal lobe, it's like a lot of territory. How do all of those areas contribute, right? What is their different function? When do they do it? So there's a lot of questions that continue to remain unclear.
That's a great answer. I'm looking forward to the TMS study.
Yes, me too. We had a grant to do it, and then COVID. But yes, it's hard work. It's hard work to do for various reasons methodologically, but it can be done.
Right. There's another question from Ayrton Brider. I'm not sure if I'm pronouncing it correctly. I'm not sure. Can you read the question, or shall I read it for you?
Do you want me to read it?
You can read it if you want to.
Yeah. Okay.
Yeah.
Regarding the cognition of people who are blind, do the studies observe differences between the computations of the two categories of verbs and nouns syntactically and semantically? Okay, that's a really cool question. So this is actually right. So the question could be about the fMRI studies or the behavioral studies. And so I will try to say something a little bit about both. So in the case of the behavioral studies, so let me open that slide. This study, right? So looking at light emission and visual verbs, these verbs belong, these distinctions that people who are blind know, these verbs belong to the same general grammatical class. So verb like look, watch, gawk, peek, glance, leer, they're not very different grammatically. So it seems like it's like the blind participants know the manner of these verbs, right? So it's not that the blind people are just knowing like the gross grammatical distinctions. However, right, as we know in language, the grammar and the meaning are very tightly interwoven. And in fact, there's a lot of work by Lila Gleitman and other people who have followed in her footsteps, showing that children use grammar to acquire the meanings of verbs. And so whether there's some subtle differences in the grammatical usage of these verbs that provide clues to blind people about their meaning, that's an interesting question that I don't know the difference to. And maybe the linguists could provide some hypotheses about it. With regard to the fMRI data, again, there's kind of interesting questions about whether the parts of the brain that are responding more to verbs than nouns in blind and sighted people, why are they doing that? Is that because of their mean different things? The verbs and nouns have different meanings? Is it their grammatical properties? And I would say that the available work that I know of suggests that it's probably a little bit of both. So in other words, this part of the brain is sensitive to the grammatical properties of the verbs, but also to their semantic properties. So the decoding results that I'm showing you here, again, is like between light and sound verbs. Those verbs are grammatically chosen to be quite similar. They're emission verbs, but one is light and sound, and you can, or hand and mouth verbs, right? Those verbs are chosen to be pretty grammatically similar, but they're different effectors. So there's sensitivity to the meaning distinctions, but also to the grammar. And we've done some analyses to show that there's some sensitivity to the grammar as well. One clue is that at least in sighted people, this part of the brain also responds to event nouns like hurricane, which suggests that maybe it's really sensitive to events, but actually it responds to the most to verbs, then event nouns, and then object nouns. So I think it's really a mix of the semantic and the grammatical. I hope I answered the question.
To me, it makes sense.
Yes, I think so. I think
if you look at if you look at studies on, for example, argument grid verbs, things like that, they also tend to engage similar areas. Right. Another question was from Claudio, and he was curious about the slide you didn't talk about, but he saw it in passing, about Ellen Keller.
Yeah.
And he was wondering whether you could say something about that. I think he was specifically interested in acquisition, but I don't know if you're going to talk about it in that sense.
Yeah, I mean, I think Helen Keller is just this amazing, interesting person. If you haven't had a chance to read her biographies, they're just fascinating. If you're interested in this topic, it's really something to do. And of course, she's this individual who she was born sighted and hearing, but then she was ill when she was about 2.5 years old and lost both her hearing and her vision. But then learned a tactile alphabet through which she communicated with a teacher and then with various assistants, and became a public speaker, wrote books. So I think she is a living testament to the ability of the human mind to get information from the world through language, because her main way of learning about the world was through verbal communication with other people. It's just that it was not verbal communication through audition or vision. It was verbal communication through touch. So yeah, I mean, I think, we as psychologists, and we get into these, we're interested in the details of how things happen, but then there are these like real life cases of humans acquiring language and meaning that I think challenge our theories that we should think about more deeply, because I think a lot of the hypotheses that we have about, the importance of particular sources of information just cannot possibly stand up to just these real life scenarios like Helen Keller. So, yeah.
All right. Thank you very much. That was a great answer. There is one more question, and I think that could be our last question. And this is a question by Ricardo Antônio de Castro Barbosa, and he is asking, what about people that are not completely blind, say with 15% of vision? Can we use or infer these data?
I think that's a great question. And it's kind of always been in the back of my mind, which is, so for example, in the case of plasticity in the visual part of the brain, does that part of the brain, how much vision will prevent it from taking on some other functions, right? And we don't know the answer to that question. So we really don't know. One hypothesis would be that any vision at all, this part of the brain is very biased to do visual perception. Any vision at all will prevent it. Another hypothesis is no, actually, maybe it's more a continuous phenomenon. So maybe somebody who is severely visually impaired and sees very little, maybe there's actually this like competition between the visual information and information from these other sources. And in fact, the other information can win out and push out visual information, actually making it harder for them to see. So that could be a clinically relevant possibility, but we actually don't know the answer to that question. So yeah, somebody needs to do that study where they scan on the same tasks people who have low vision, because of course I talk about people who are blind as if it's like a category, but actually we are studying a very small proportion of people who are blind who really have very minimal light perception or none. But there's a lot of people who are visually impaired, and there's a question about how things work for that population. Yeah. I hope I understood the question. Yeah.
I think you did. It gave me other ideas, but I think we have to finish because we've been talking for 1.5 hours. This just goes to show that it's an extremely fascinating topic to talk about and to learn more about. So I think we can only thank you for your wonderful talk. And I mean, if anyone has any questions, feel free to post them in the chat afterwards.
Or to contact me. Yes, I'd be happy to. Love talking to you. It's so great. Yeah, thank you so much.
Oh, that's great. And remember that the video remains available online. So if you want to, review some things or see, check some things, you can look again. You can look at it again. All right. Thank you so much, Marina.
Bye.
Thanks everyone for watching, and see you next time on Linguistics.
Thank you.
Ela saiu. Foi ótimo, né, Maré? Muito bom.
Mas eu acho que ela saiu também sem querer. Foi meio que, assim, tipo, apertou esse botão e...
Ela apertou o Leave Studio.
Isso aconteceu comigo também quando eu tentei entrar. Então foi ótimo, é sempre um pouco assim, tipo, né, assim, você não consegue comunicar muito direito, isso sempre atrapalha um pouco, mas eu acho que tudo deu certo.
E a gente que está aqui fica mais difícil, né? Todas as vezes que eu transmito eu tenho que rever. Porque é tanta coisa que fica tomando conta.
Eu acho que a próxima vez o que a gente poderia, assim, avisar para a pessoa, mas isso depende um pouquinho também da flexibilidade de quem está apresentando, mas eu faço isso. A live, você está ao vivo? Por favor, ao vivo.
E